Welcome to Bedtime Astronomy. Explore the wonders of the cosmos with our soothing Bedtime Astronomy podcast. Each episode offers a gentle journey through the stars, planets, and beyond, perfect for unwinding after a long day. Let's travel through the mysteries of the universe as you drift off into a peaceful slumber under the night sky. This week in astronomy, microquasar acceleration, dark matter detection, and machine learning in gravitational waves. Microquasars, hidden cosmic accelerators. Earth is constantly bombarded by particles originating from outer space. While people are mostly familiar with rocky meteorites from within our solar system, which create the brilliant streaks of light known as shooting stars, it is the much smaller particles that provide scientists with deeper insights into the nature of the universe. Among these particles are subatomic ones, such as electrons and protons, which arrive from interstellar space and beyond. These high-energy particles, known as cosmic rays, are among the fastest-moving particles in the universe. Despite their known presence, the origins and mechanisms that accelerate the most energetic of these cosmic rays remain one of the biggest unanswered questions in astrophysics. One of the most promising locations for particle acceleration is in the relativistic jets launched from black holes. These jets, which expel matter at nearly the speed of light, are thought to provide ideal conditions for accelerating particles. However, the details of how these acceleration processes occur and under what specific conditions they take place are not yet fully understood. Within our galaxy, some of the most powerful jets are found in systems known as microquasars. These systems consist of a stellar mass black hole in close orbit with a normal star. When the two objects are near enough to each other, the black hole begins pulling in material from its stellar companion. This process fuels the formation of jets that are ejected from the region surrounding the black hole. Recent studies suggest that microquasar jets are efficient at accelerating particles. However, it remains unclear how much these systems contribute, as a group, to the overall amount of cosmic rays in the Milky Way. Answering this question requires determining whether all microquasars have the capability to accelerate particles or if only certain systems possess the necessary conditions. Microquasars are typically classified into two categories based on the mass of the companion star, low-mass and high-mass systems. The low-mass systems are far more abundant in the galaxy. However, up until now, evidence for particle acceleration had only been detected in high-mass microquasars. One well-known example is SS433, which was recently identified as one of the most powerful particle accelerators in the Milky Way. This system features a companion star with a mass approximately 10 times that of the Sun. Because no previous observations had detected particle acceleration in low-mass microquasars, it was widely believed that they lacked the necessary power to produce high-energy gamma rays. This assumption has now been challenged by a groundbreaking discovery made by Dr. Laura Oliveira Nieto from the Max Planck Institute for Nuclear Physics in Heidelberg, Germany, and Dr. Guillaume Marty de Vessa from the University of Trieste in Italy. Their findings, published in the Astrophysical Journal Letters, provide the first evidence that a low-mass microquasar can accelerate particles to extremely high energies. The researchers analyzed 16 years of data collected by the Large Area Telescope, LAT, aboard NASA's Fermi satellite. Their study revealed a faint but significant gamma-ray signal originating from GRS 1915+105, a microquasar with a companion star that is smaller than the Sun. The detected gamma rays have energies exceeding 10 giga-electron-volts, GeV, suggesting that this system is capable of accelerating particles to even higher energy levels. The data strongly support a scenario in which protons are accelerated within the microquasar's jets. Once these protons escape the system, they interact with the surrounding gas, producing high-energy gamma-ray photons. To further support this theory, the researchers also used observations from the Nobayama 45-meter radio telescope in Japan. These data confirm that there is an ample amount of gas material surrounding GRS 1915+105, making it possible for escaping protons to generate gamma rays in the expected manner. This discovery has major implications for astrophysics. Since low-mass microquasars are far more numerous than their high-mass counterparts, this finding suggests that microquasars as a whole could be a much more significant source of cosmic rays in our galaxy than previously estimated. Despite this breakthrough, many questions remain. Not all microquasars appear to be efficient particle accelerators, and it is still unclear why only certain systems exhibit this behavior. More detections, along with multi-wavelength studies across different types of radiation, will be necessary to understand the specific conditions that enable some microquasars to accelerate particles so efficiently while others do not. Space experiment aims to detect dark matter. Scientists are embarking on an ambitious space experiment to investigate one of the greatest unsolved mysteries of the universe, dark matter. Despite making up an estimated 85% of all mass in the cosmos, this elusive substance remains invisible and undetectable through conventional observational methods. Now, a team from the University of Southampton has developed a novel approach that could advance our understanding of dark matter by measuring its potential interactions in the vacuum of space. The researchers have designed and begun testing a device that detects extremely small forces by firing lasers through levitating graphite sheets in a zero-gravity environment. According to physicist Tim Fuchs, the project could lay the groundwork for future space-based experiments that may finally provide direct evidence of dark matter. He highlights that, although numerous theories exist regarding its nature, no Earth-based experiment has ever succeeded in detecting it. Dark matter plays a crucial role in shaping the structure of the universe, yet its presence can only be inferred through its gravitational influence on visible matter. First identified in the 1930s, it does not emit, absorb, or reflect light in any meaningful way, making it impossible to observe with traditional telescopes. The motion of stars and galaxies suggests the presence of an unseen mass exerting gravitational effects, which is attributed to dark matter. The experiment proposed by the Southampton team is unlike anything attempted before. Their method involves suspending graphite particles between magnets. In the absence of gravity, this setup becomes highly sensitive to even the smallest external forces. If dark matter exists at a high enough density, it could generate a subtle yet measurable wind, gently pushing the levitated graphite particles. Detecting this movement would provide the first direct measurement of dark matter interactions. The experimental device, weighing only 1.5 kilograms, will be sent into space as part of the Jovian 1 satellite mission, a collaboration between Space South Central and the Universities of Southampton, Portsmouth, and Surrey. The team is currently evaluating different launch options, with the goal of deploying the satellite early next year. Once in low Earth orbit, the device will conduct its tests over a 2-year period, analyzing the movements of the levitating graphite in response to potential dark matter interactions. Fuchs points out that one possible reason for the lack of success in Earth-based dark matter experiments is the interaction rate hypothesis. Some theories suggest that dark matter might interact with ordinary matter so frequently that it cannot penetrate Earth's atmosphere or the underground locations where many major detectors are placed. If this is true, then space-based detection could provide the breakthrough scientists have been searching for. This mission is the first of its kind to apply levitation technology in space for dark matter detection. If successful, it will serve as a proof of concept, demonstrating that direct measurements of dark matter interactions are possible outside of Earth's atmosphere. This innovative approach could pave the way for future space-based experiments, bringing science one step closer to solving one of the deepest enigmas of modern astrophysics: gravitational wave detection with machine learning. Researchers at the University of California, Riverside have developed a new machine learning approach to improve data analysis for LIGO, the Laser Interferometer Gravitational Wave Observatory. This method enhances the ability to detect patterns and reduce noise in the vast and complex datasets produced by the facility, helping scientists refine gravitational wave observations. The approach could also be applied to other large-scale scientific experiments, such as particle accelerators and industrial systems that generate massive amounts of data. LIGO is designed to detect gravitational waves, ripples in the fabric of spacetime caused by the movement of extremely massive objects, such as merging black holes. The observatory was the first to confirm the existence of these waves, providing key evidence for Einstein's theory of relativity. It consists of two 4-kilometer-long interferometers in Hanford, Washington, and Livingston, Louisiana, which work together to capture these cosmic signals by measuring tiny distortions caused by passing gravitational waves. These detections offer a new way to study the universe, shedding light on the nature of black holes, cosmology, and the densest forms of matter. The challenge, however, lies in distinguishing real gravitational wave signals from noise. Each LIGO detector records data from thousands of environmental sensors, which track factors such as seismic activity, atmospheric disturbances, and human-made vibrations. These external influences can introduce noise into the system, affecting the quality of the data and sometimes causing glitches, brief bursts of unwanted signals that interfere with gravitational wave detection. To address this issue, the UC Riverside team developed a machine learning tool capable of identifying patterns in the data without human supervision. The system was designed in collaboration with LIGO operators and engineers, ensuring its practical application to real-world data. The results showed that the model was able to accurately recognize environmental states, such as earthquakes, ocean waves, and human-generated noise, without any prior input from researchers. This capability makes it a powerful tool for isolating and understanding noise sources, ultimately leading to improvements in LIGO's sensitivity. The machine learning algorithm works by analyzing signals from over 100,000 auxiliary channels at the LIGO sites, which includes sensors like seismometers and accelerometers. These instruments monitor the surroundings of the interferometers, recording environmental conditions that might influence detections. By clustering and classifying data points, the tool can link specific noise events to external sources, helping scientists pinpoint the causes of certain glitches. The team presented their findings at the IEEE's 5th International Workshop on Big Data and AI Tools, Models, and Use Cases for Innovative Scientific Discovery, held in Washington, D.C. Their research paper, titled Multivariate Time Series Clustering for Environmental State Characterization of Ground-Based Gravitational Wave Detectors, is available on the AR14 preprint server. One of the key breakthroughs of this research is the public release of a large dataset used in the study. This dataset, made available with the cooperation of the LIGO Scientific Collaboration, allows other scientists to validate the results and develop new data analysis methods. Given that most scientific datasets of this nature remain proprietary, this release is expected to foster interdisciplinary research in machine learning and data science. By working through all LIGO data channels for over a year, the team identified links between environmental noise and the occurrence of glitches in gravitational wave detections. This discovery could lead to strategies for preventing or mitigating noise sources, improving the accuracy of LIGO's observations. The research also highlights how machine learning can assist in detecting new patterns in large-scale scientific experiments. The long-term vision for this tool is to enable researchers to identify unknown noise sources and guide practical improvements in LIGO's design. By recognizing patterns in environmental data, scientists can make targeted changes, such as replacing components or adjusting sensitivity settings, to minimize interference. This approach paves the way for more accurate gravitational wave detections and deeper insights into the most extreme cosmic events. In addition to the UC Riverside team, the research involved contributors from the LIGO Livingston Observatory and included distinguished physicist Barry Barish, a leading figure in the field. The project represents a significant step forward in the intersection of physics, data science, and artificial intelligence, demonstrating how advanced computational techniques can enhance our ability to explore the universe.